Hi, welcome to today's webinar on compressed air. My name is Steve Koski. All of PGE's seminars and webinars are sponsored in part by the Energy Trust of Oregon. We work together to make sure the recommendations and concepts you learn in our events are consistent across all of our individual programs and services. So to get us started, let's take a minute and use our markup tools, and let's mark the operating compressor horsepower that you have in your system on the left, and then mark what kind of compressors you're using on the right. Somebody who doesn't have a compressor. Okay. Some small and some small mid-sized systems. Well-flooded screw, a couple of those. Well, free screw, will make things interesting. Okay, excellent. Okay, another smaller system, perfect. Well, that's who this is aimed at, so right on. So here's our basic path today, but I'm happy to take any rabbit trails off to the side and answer any questions that might pop into your heads as we go. In fact, that'll make today's presentation more valuable if you ask questions that deal with your specific situation. So feel free to send Beth a chat message. And if everyone could come up with one question or more, that would be really great. So first we're going to talk about how compressed air is great. Then we're going to talk about how it's also kind of terrible at the same time. Then we're going to go through a list of generic ways to save energy on any system. Then we'll spend the bulk of our time on 5 case studies where folks cleaned up their compressed air systems and saved energy. At the end, we'll point you to some technical resources and financial help, and then we will sum up. So compressed air is wonderful. It can do about anything. It can push, pull, carry, cool, stir, dry, and last but not least, it can disappear. It's very easy to work with. It's simple to connect. It won't shock you. You don't need an electrician. It works in wet and corrosive hostile locations. Compressed air actuators are low cost, light, and small. And compressed air spills are self-cleaning. In fact, compressed air is so wonderful that 10% of the power generated in America goes to air compressors, which is kind of a phenomenal fraction. All the gas, coal, solar, wind power, hydropower, 1 dime out of every dollar that is feeding an air compressor. And 7 of 10 industrial sites have compressed air. But it's also, so it's pretty versatile and simple to work with, so what's the problem? Well, it's also kind of terrible. Air is very compressible, which means that when we compress it, a lot of the energy turns into heat. So let's all do a thought experiment together. Hold your hands out in front of you and grab about a gallon of air between your hands. Now squish this gallon of air down to a pint. So this is an 8-to-1 compression and would give you about 100 psi. Now if you could do this and not let any heat escape, how hot would that pint of air be? So let's guess at the temperature of this pint of air, and let's type it on the screen. So click on the annotation tool and then click on the text tool, and just somewhere on the screen click and type a number of degrees Fahrenheit that you think this pint of air would be after we squished it with this 8-to-1 compression. Or you could just use the marker tool and just kind of write your number out on the screen. Okay, 200 degrees. We're seeing some answers come in. Oh, I shouldn't have said that. We're going to influence everybody.
Make sure, just want to remind people, make sure after you type the number that you click somewhere else on your screen so that everyone else can see it.
Oh, yeah. Yep, so type your number, then click somewhere else. 200 degrees Fahrenheit, one guess, another 125. 100 degrees, 1,000 degrees, there we go. 150 degrees, so. Okay, excellent. Amazingly enough, if we could do this, if we could actually do this and not let that heat escape, our pint would be 500 degrees Fahrenheit. Well, but why aren't our pipes and our tanks and hoses, why isn't everything touching our compressed air system 500 degrees? Well, it's because we've thrown away this heat of compression in oil coolers, intercoolers, and aftercoolers. 85% of compressor power gets turned into heat. That means 100 horsepower makes 100 horsepower compressor makes 85 horsepower of heat and 15 horsepower of usable air power. Now that's the best case. It could actually be a fair amount worse than that. So one way to think of an air compressor is a fancy heater that makes some compressed air as a byproduct, because it's mostly making heat. So to get 15 horsepower of air power to the shop floor for a year, we could do it for $50,000 using an air compressor, or if we could do it directly with an electric motor, it would only cost about $7,500 a year. So what is the lesson? Compressed air is expensive. We want to use it carefully, and we want to make it efficiently. So now on to some generic energy-saving concepts. These are relevant to about any system, whether it's lighting, irrigation, refrigeration, or anything you can think of. So concept one is minimize loads. We want to reduce the demand on the system, which in our case means reducing the amount of compressed air we use. If it was refrigeration, it would mean reducing the heat load. If it was pumping, we'd try and reduce the total gallons of water that were required. Number two, use your best part load option. Most equipment is pretty efficient when operated at 100% capacity, but its efficiency can drop off radically when we only need 50% capacity or 10% capacity. But many times there are alternate ways to control a piece of equipment so that when it's at low capacity, its efficiency is still reasonably good. Number three, turn it off. I think this is self-explanatory. Let's get idle equipment shut down and isolated when it's not needed. Number four, minimize pressure drops. In compressed air, sometimes we have a bad actor that will have a high pressure drop across it, and which forces us to operate at higher pressure in order to compensate for this guy. And this could be a plug filter, undersized piping, or things like that. Optimize pressure settings. So we need enough air pressure to get the job done, but excess pressure just kind of increases compressor power and increases leak flow. Number six, keep idling time to a minimum. This is kind of like number three. We generally can't instantly shut off most air compressors, at least not screw compressors, but we can set up the automatic controls to shut them down automatically and then restart them automatically when needed. Right technology. So from time to time we see someone using the wrong technology for the job. This can cause the system to be just fundamentally inefficient and use much more power than is necessary. So one example would be using a desiccant dryer to provide super dry air when it's just not needed, or using some cheap tubing fittings that end up developing a lot of leaks. Number eight, right size equipment. So undersized equipment won't get the job done, and plants are pretty good about buying more compressors if the plant air pressure is chronically low. So undersized equipment isn't typically the problem. But occasionally we find systems that are much larger than needed, which forces them to operate at low capacity, where their efficiency could be pretty bad. Number nine, remove barriers to more efficient set points. That's fairly self-explanatory. And number 10, make the most of your controls. Often systems already have efficient controls in place that just aren't being used. if they don't have the controls in place, oftentimes your best buck is to just upgrade the controls, and you can get a pretty good energy savings out of that for your dollar relative to replacing the equipment outright. So let's move into some case studies of some small industrial systems. So our first study here is a shop air system. They're running two 10-horse reciprocating compressors, piston compressors, and they alternate compressor operation every week with a lead lag switch, and the lead compressor is running about 60% of the time during the week, and they have a non-cycling refrigerated dryer. Now, reciprocating compressors are typically 25 horsepower and smaller, and they usually use start-stop controls, which is great because the less air you use, the less time they spend on. They have what we call perfect part load performance, meaning that at 30% capacity, they use 30% energy. A non-cycling refrigerated dryer uses a constant power regardless of how much air is being dried. And this can be okay for small systems and small dryers, but could be an energy penalty in medium and large systems. And dryer manufacturers also make what's called a cycling refrigerated dryer, which basically matches the dryer power to the air demand. And so at low air use, they don't use very much power.
Steve, this is Beth. When you say refrigerated dryer, it makes me think of a refrigerator. Is that anywhere near the case?
Yeah, that's right on. So a refrigerated dryer has a small refrigeration system in it, just like a fridge or an air conditioner. So this cools down the air, then the condensed water is stripped off, and then there's a little heat exchanger that warms up the outgoing air. And refrigerated dryers are great when the air users are indoors and when like ultra pure isn't needed for some pharmaceutical or high-tech use. And refrigerated dryers can provide air that has a dew point of about 35 to 40 degrees Fahrenheit. Now, if you need drier air, the next step up is a desiccant dryer, which produce air that has about a minus 40 degree dew point. So, colder than you're likely to ever see even outdoors, at least in the western United States. So there are several kinds of desiccant dryers, and they're all much more expensive to buy and operate than a refrigerated dryer. So in general, refrigerated dryers are our friends, and we want to use them whenever possible. Now in the shop, they're using pneumatic tools. They're also have some machining operations, so they're blowing some parts off from time to time. They also have this bucket of glue that they keep mixed up with an air-powered mixer. Just sits there and turns a paddle slowly and keeps this glue from setting up. And leaks. They can't shut off this compressed air system on nights and weekends due to this bucket of bonding agent. They got to keep that mixer going. And this system costs a little bit over $4,000 a year to operate. So for upgrades, what these guys went after is they went after a handful of known leaks. They also installed an explosion-proof electric mixer for this bonding agent. That was about $900. And then they shut off the air on nights and weekends. Now you might be wondering what an explosion-proof electric mixer is. That's just kind of a term that we give a piece of equipment that, so there's potentially some flammable fumes that are coming off of this glue that could potentially be lit by an electric motor. And so an explosion-proof mixer basically just has a strong enough housing that if these fumes happen to ignite, that it's not going to go flying apart and injure people. So that they can use, just a direct electric motor rather than this air-powered mixer. Now, this managed to get their electrical costs from over $4,000 a year to $1,500 a year, which saved them, just shy of $3,000 a year in electrical power. As far as getting the air shut off on the nights and weekends, I mean, this just involves some explaining, training, and some follow-up. And after a few weeks, it became second nature for the foreman to shut off the air at the end of the day and then to start it up again in the morning. So now let's think back on our 2 by 10 horse reciprocating compressor shop air example. What concepts did these folks use to capture energy savings? Use your marker or the arrow or whatever you like, and let's check off some of the principles that are in action on this case study. Go ahead and color this up. Yeah, turn it off. That's definitely a big one. Getting that off nights and weekends rather than just feeding leaks. Yep, right technology, exactly. That electric mixer allowed them, first of all, it uses a ton less power, and then it allowed them to do number 3, to turn it off and minimize loads. Yep, exactly. Okay, now let's talk about a chemical plant. These guys were operating a 75-horse modulating compressor that produced as much as 360 CFM, and a heatless desiccant dryer that's rated at 500 CFM. And they have a handful of air users all inside the building, and this system's almost $31,000 a year in electricity to operate. Inlet modulation is the type of compressor they were using, the type of control, and this controls the air pressure in the plant by simply closing down the inlet valve and choking off the flow into the air compressor when less flow is needed. And inlet modulation will reduce compressor power a little, but not very much. You can see at 0 capacity, the compressor is still using about 70% power, and even at 50% capacity, our compressor is still using something like 85% power. So inlet modulation is a low-cost way to control an air compressor. It's fine if the compressor is going to be fully loaded or near full load. There's not much energy penalty. Variable speed control uses a drive to adjust the speed of the screws to alter the flow that the compressor is making, and it has significantly better part load performance at reduced load. But there's a cost premium, for the drive and the additional engineering that goes into that compressor. So in this case, the compressor would use, about 50% power if it was operating at 50% load. Okay, so who's using the air in this chemical plant? So some of the users is this oversized dryer. Well, let's talk about, the dryer problems. First of all, the dryer's too big. It's rated at 500 CFM, but the compressor is only 360 CFM, and the dryer has no purge controls. So this dryer is continually purging at 14% of its rated flow. Not 14% of its actual flow, it's continually purging at 14% of its rated flow. So that's 70 CFM, which ends up being like 19% capacity this compressor has to operate just to satisfy the dryer, just to keep the dryer functioning. But the plant didn't really need the minus 40-degree dew point from a desiccant dryer. The users are inside the building, so a plus 40-degree dew point from a refrigerated dryer would be just fine. They had a couple proposals from 2 different vendors. Vendor 1 had some older data, and they had proposed, putting in a 100-horse variable speed compressor and adding a heated desiccant dryer with purge saving controls. Now a heated dryer is a little more efficient than a heatless desiccant dryer, but it still uses a lot more power than a refrigerated dryer. And that was their second proposal, was vendor 2 says, look, let's put in a 75-horse variable speed compressor, and let's just put in a cycling refrigerated dryer, because we all can see that you don't need this super dry air. So that's what they did, 75-horse variable speed compressor, cycling refrigerated dryer. Not a cheap project, $49,000, but they ended up getting half of the money a return to them, in the form of a rebate from the utility program. So, only $24,000, $25,000 net cost for the plant. Then this gave them a savings of almost $19,000 a year. So after that utility incentive, they're at a little bit over a year payback. So pretty good economics for that project. Okay, thinking about the chemical plant, what concepts did they use to capture energy savings? So go ahead and mark this screen up with whatever you think was appropriate. And feel free to double mark. If someone else has your idea, you can mark it too. Yeah, use your best part load option. So getting from modulation to speed control, save them a good amount of energy. Yeah, and right size equipment and right technology. Yeah, the dryer, the first desiccant dryer was just too big. And even if it was the right size, it was kind of the wrong technology for their needs. Yeah, and by getting away from that minimized loads, exactly. If that 15 horsepower worth of compressed air that dryer was consuming didn't have to be made if we went to a refrigerated dryer. Excellent. Now let's look at a water treatment plant. A little different situation here. We have a 60-horse modulating compressor on one system, and then there's a completely isolated system about 200 yards apart that's running a 30-horsepower compressor that uses load-unload control. And to operate these two compressors costs about $30,000 a year. Now, a study was done, and it showed that a single 60-horse compressor could make enough air to satisfy both of these systems. But there was the potential to have, to connect these systems could be quite expensive. 200 yards of piping, depending on where it's going, could be prohibitive. But this plant actually did their own piping work internally with in-house labor at a reasonable cost. So that's exactly what they did. They piped the two systems together, and they actually completely eliminated the 30-horsepower compressor, had that hauled off-site, and they installed a new 60-horse variable speed compressor. Now, they probably didn't have to do this. They could have just kept the old compressor, and they would have been just fine. But this gave them some additional savings. And it allowed them to also still kind of have a backup compressor. Keep that old, less efficient guy there in case the main one is down for maintenance. $60,000 project costs. Once again, these guys got a 50% incentive from the utility. So about a $30,000 net project cost to a savings of about $14,000 a year. That's what, about a 2.1 year payback project. Not bad economics. Okay, let's get ready to mark. What did the water treatment plant do to save energy? Now, this is a little tricky. Because, by combining systems, they went from 2 operating compressors to 1. So I can see elements of 3 in play here. Turn it off. And the variable speed compressor saved energy, so I can see elements of 7. And yeah, right size equipment, I can see that too, because they were basically oversized. And use your best part load option. Yep, I can see that too. And oftentimes if we have 2 pieces of equipment trimming, operating at part load, getting down to 1, that can save us energy. Yep, remove barriers and make the most of your controls too. Very good. All right. Now a system that was designed for one thing and ended up being used for another. I think we have 2 examples like this today. So this system was designed to serve 2 machine shops and a dock. they had a 75 horse compressor that used load-unload control, and it's designed to serve the dock and the 2 machine shops. These guys are only a day shift operation, so they already shut the compressor down nights and weekends. And you can see, even though this is a fairly big compressor, they don't have outrageous annual operating costs because their hours are kind of low. But what happened is shortly after the system was designed, the dock was no longer in use, and the staffing in both machine shops were reduced. And if you looked at the machine control panel and looked at the total hours versus the loaded hours, you can see that this compressor is only averaging about 10% capacity. So this compressor is spending like 90% of its time unloaded. So what's the problem? Well, a fully unloaded screw compressor still consumes somewhere between 20 and 50% power. So that's like 15 to 38 horsepower being consumed when not making any air. So the upgrades these guys went after is the logging showed that, look, a 15 horsepower reciprocating compressor is going to be just fine. And grand total cost for this project was $6,000 with freight and installation and everything. And I was always kind of amazed because you think, well, $3,400 a year, that's not an outrageous cost. But look, they were able to lower that to $1,000 a year and save $2,400. So even though you might not be spending a fortune on compressed air, if you're doing something fundamentally inefficient, you might be able to save a lot of that power. So the reciprocating compressor, it's a bit less efficient at full load. It's, CFM per kilowatt is a little lower than a screw compressor, but it has the advantage of using, absolutely no power when it's off, which our other compressors won't do, or when it's unloaded, because it really doesn't unload, it just shuts off. So for machine shops, a reciprocating compressor can be the perfect fit. Okay, what ideas did the machine shop use to save energy? Yeah. Number 2, use your best part load option. Yeah, so that plays into it for sure. And the right size equipment, that's a pretty heavy hitter here, is a 75 horse compressor when we only need 10 to 15 horsepower worth of air. And right technology, yep, a load unload screw is probably not the best choice for a little machine shop, especially if it's oversized. Yeah, keep idling time to a minimum because the new compressor doesn't even idle, it just shuts off, which feeds into number 3 there also. Okay, excellent. Now we're going to talk about another case study, which is a compressed air system that's making air for a palletizing system. So a palletizer is taking cases of product off of a conveyor belt and stacking them on pallets. And these guys are operating a 30-horse oil-flooded screw compressor.
Steve, when you say oil, I don't know what an oil-flooded screw is. Can you explain that?
Yeah, we probably should have talked about this earlier. There are 2 basic types of screw compressors. There's oil-flooded and oil-free. In an oil-flooded screw, we inject some oil into the rotors, and the oil absorbs a lot of heat. It also helps seal up the gaps between the rotors and the housing. And after the air is compressed, it goes through a sump or an oil separator. There's a coalescing element inside the sump, and hopefully all the oil gets stripped out of the airstream, and the oil stays in the compressor to be reused, and the air goes to an aftercooler and then off to the filters and the dryer. An oil-free compressor doesn't inject any oil, and so they don't have a sump or an oil separator. And the other big difference is there are 2 sets of screws in an oil-free unit. There's 2 stages of compression. So the first stage compresses the air up to like 25 or 30 psi and about 300 degrees Fahrenheit. Then there's an intercooler where the air gets cooled down, and then it's brought into the second pair of screws where it's compressed up to the final pressure. There's no oil anywhere that contacts the airstream, so there's inherently less risk of getting contaminants into the air supply. The downside with the oil-free compressors is usually cost. They cost about twice as much as an oil-flooded compressor. There's 2 sets of screws, and I think the machining tolerances are tighter. Now, their air pressure. Oh, well, before we get to that, let's talk about they're operating this compressor in hand mode. They have a handoff auto switch, and they've just always operated it in hand as long as anyone can remember. They don't even really know what these switches mean. They just, the compressor is used in hand, which actually for this type of compressor means that it's just going to modulate. It won't let the compressor unload. And they also have a heatless desiccant dryer, which oddly enough we found had been valved off. The purge air had been valved off to it, so it hadn't been able to regenerate for at least 3 weeks since the last service was done on it. And their air pressure, I don't know if you can see this very well, but you can see they're operating 120, it looks like 129 pounds on this gauge, 125 to 130 pounds air pressure. The users are primarily this palletizing equipment. It's in a refrigerated area, so this space is, 40 degrees. The dryer is also a significant user, so this dryer is going to purge at 14% of the rated flow once we get the valve opened. And leaks are also a consumer, and $11,000, $12,000 a year to run this system. So the upgrade here was fairly simple. They basically just put the compressor into the automatic mode, and they hung a big sign on the compressor. Use auto mode, do not use hand mode. And they also reduced the load and unload pressures to match what the air users needed, which was they needed about 90 psi to function properly. And so this cost them almost no money because they just had the technician do this on his next regularly scheduled visit. And this saved them $3,300 in electricity per year by moving from modulation control to load-unload control with really no other changes. They didn't change out the dryer, didn't go after leaks or anything. So yeah, so our modulation part load performance here, and case 1 of load-unload would be down here. That'd be a pretty good example of load-unload control where it's being done well. Case 2 is kind of a lousy load-unload. It's where it's not saving as much energy. Now, when a screw compressor unloads, the inlet valve closes or nearly closes, and a sump blowdown valve opens to relieve the pressure in the sump. And that sump pressure determines the compressor power. So if the sump blows completely down to atmospheric pressure, you could have 18 or 20% power when the compressor is fully unloaded. But many compressors won't let the sump blow all the way down. They don't quite close the inlet valve, and they'll hold 20 to 50 psi in the sump. And they use that pressure to push oil through the compressor. And these could have, 30, 40, 50, even as high as 50% power when the compressor is fully unloaded. Yeah. The other thing that can influence whether you're in kind of a case 1 situation or a case 2 situation is how much tank volume you have. If you have very little tank volume and the compressor is loading and unloading very quickly, it's spending a lot of time blowing down and loading back up. Whereas if we have more tank volume, we spend less time in these transitions and more time, fully unloaded or loaded. So with a palletizing system, what techniques are these guys using to save energy? Yeah, optimized pressure settings. We don't need to make 130 pounds if our users are happy at 90. And use your best part load option. Yeah, they had the controls there. They just didn't really know it. So they just had to, yep, use your best part load option, make the most of your controls. Excellent. Okay, a little different story here. There's a coffee roaster with a booming business. They started with a little 5 horsepower reciprocating compressor. And a little while later, they bought a 10. They were out of air, and they bought a 10-horse reciprocating compressor. And then a few months later, they needed more air, and they bought a 15-horsepower reciprocating compressor. And they just Frankensteined these all together. The compressors were in bad locations. They're running almost constantly. They're noisy. They're bad locations. And they needed to get the compressors off of the production floor and into a compressor room and move to a single compressor. And move to a screw compressor, kind of for their type of air use. So the vendor says, all right, here's a low price bid for a 40-horse modulating compressor. Because, you know, vendors want to sell equipment, so sometimes they don't always offer their premium options because they want to get the sale. And so if the high price option might not get selected. So the utility program, someone caught wind of this and said, hey, let us help you upgrade to a variable speed compressor. Now the difference in cost to move up to a variable speed compressor was $9,000, which is, you know, it's a pretty steep price to pay when you're only buying a 40-horse compressor that's not, I mean, $9,000 is like a 25% increase in cost. But the utility ended up paying for about half of this cost upgrade. So the cost upgrade only ended up being about $4,500, and this saved them $1,900 per year. So what did the coffee roaster use to save energy? Yeah, right technology, definitely. Right size equipment. Maybe a variable speed, use your best part load option. They did upgrade to that. There's probably a number 11 that's missing from this list, which says take advantages of efficiency upgrades during equipment purchases. Because, I mean, that's the best time to really improve your efficiency position is when you're buying new equipment. So excellent. Now, so compressed air is a very big world with lots of complexity, but thankfully there are some good routes for assistance. A PGE and the Energy Trust have free energy efficiency services. Visit portlandgeneral.com/business, or commercial customers can contact Paula Conway, listed on the slide here, and industrial customers can contact Darren Spencer. If you're not a PGE customer, contact your local utility for assistance.
And instead of Darren Spencer, that would be Stacy Milliman.
Aha. So let's sum up here. Compressed air is really wonderful, but it's fundamentally inefficient. So most of our compressor energy turns up into heat, which we usually can't use and have to throw away. So we want to use compressed air carefully, and we want to make it efficiently. And let's hand it back to Beth for some questions.
Thank you, Steve. And before we proceed to Q&A, I wanted to remind everyone that you can continue to submit questions to me through chat, and I will ask them of Steve. And Steve, it looks like our first question is, how should I sequence 2 piston compressors?
Reciprocating compressors or piston compressors, like we discussed earlier, they have kind of perfect part load control. So there's even if you do it terribly, it's still not that terrible from an energy perspective. But what most people do is they will have the settings for one compressor kind of staggered slightly lower than the second compressor. And then periodically, they will swap those two compressors. So if, let's say, one compressor is running between 100 and 120 pounds, and the next compressor runs between 90 and 110 pounds. And then you could, every month or something like that, you could switch those two if you wanted to even out the run hours on the two compressors, put the other one in the lead position.
Thanks, Steve. And our next question is, every time a compressor starts, I get a demand charge. So isn't it better just to leave it on?
I'm glad you asked that. So one of the common beliefs out there is that your peak demand charge is set by your instantaneous highest peak power use. But it's actually the way the utility structure works. It's your highest 15-minute period of energy use during the month, not your highest instantaneous peak. And so when do you get your highest 15-minute period during the month? Well, it's when everyone's at work, all the equipment's going, maybe all the air conditioning equipment's on in an afternoon or something like that. I mean, those are the type of situations that set your peak demand. When you start a compressor or start a fan or something like this, there is a period when the compressor starts that has some high power use, but it's really pretty brief. It's just a few seconds long. And so if you take that few seconds of high power use and you average it out over the 15-minute period, it kind of disappears. It becomes kind of insignificant. So it's much better for your power bill if you shut off a compressor and then restart it again 20 minutes later than it would be to just have it sitting, running unloaded or idling.
Great, that's great information. And next question is, how do I tell how much air my compressors are making?
So let's start with the easy one. So if you have a reciprocating compressor, then you can kind of just do a time study where you can go out with your watch and a piece of paper and you can say, oh, it ran for, you watch it for 10 minutes, say, and you add up the time and say, oh, it ran for 3 minutes out of this 10 minutes. And so you know that that compressor is at 30% capacity. You can do the same thing with a load-unload compressor as long as it's not using inlet modulation. You can basically just do a time study where you say, okay, during this 10-minute period, or it was loaded for 3 minutes, a total of 3 minutes, and so that would be 30% capacity also. Variable speed compressor, it'll have somewhere on the control panel you can either see the percent speed or the percent capacity, and so you can just kind of watch that for a couple minutes and say, oh, I'm running near 50% capacity or 80% capacity pretty easily there. Where it gets hard is if the compressor is using inlet modulation, because the compressor kind of sounds the same. The pressure's not really changing much, and there's no difference in noise that the compressor is making when it's at 30% capacity or 80% capacity. So if you're doing that, you're going to have to measure current or measure some pressures internal to the air compressor. That gets a little bit harder.
Great, thanks. And our next question, I have a shop that uses a few hand tools and air blow guns. I have 2 air compressors. I have a 35 horsepower oil screw and a smaller piston compressor. Which one would be better to use? My screw is a variable speed compressor. That's a story problem.
Variables, yeah, that's a great one. I like it. So which one would be better? Well, you're in a pretty good situation to use either one, because your variable speed compressor is going to have good part load performance, and if the air demand is really low, let's say nobody really uses air for very long, they will typically unload and shut down and not use any power. So that could be a good choice. Or the reciprocating, if the demand is low enough, the reciprocating compressor might be fine too. I would say you have choices between good and good there. If the demand is low enough, maybe the recip, or you could experiment. But yeah, I think you're in a good position there because you probably can't make a terrible choice.
Great, that's great. And I think we have time for about one more question, and that is, how do I know if my compressor is using inlet modulation or load-unload control?
So a lot of times a compressor, the load-unload compressors will, on the panel, they will say loaded or unloaded. And you can also kind of see the pressure rise and fall. So let's say at 85 pounds, the sound will change and the pressure will start to rise, and it'll rise up to 95 pounds, and then the sound will change again, and you'll see the pressure fall back to 85 pounds. So that's a pretty good clue that you're using load-unload control there, because you get this kind of seesaw pressure profile. Yeah, modulation can be trickier because the pressure will be steady, and you won't hear that change in sound as the compressor loads and unloads. And there's a couple brands of compressors out there that actually have a capacity gauge on them that you can look at and see the compressor capacity. So if you're using modulation and it's sitting there and it's running at, you know, some mid-range capacity and it's fairly steady, then that compressor is probably using modulation control.
Great. Thanks, Steve. And that was our last question, and I'd like to thank you all for joining us today.